Hello. Welcome to today's class. Our main objectives today are to explain intrinsic semiconductors, describe intrinsic conduction. So we begin by introducing intrinsic semiconductors. In definition, a semiconductor is a material whose electron conductivity falls in between the conductivity of metals and that of insulators. The resistance of a semiconductor towards the flow of current falls as the temperature of the environment rises. Examples of semiconductors include silicon, germanium, tin, selenium, and tellurium. We look at the properties of intrinsic semiconductors. The first property, we find that the resistivity of the semiconductor is less than that of an insulator, but more than that of a conductor. 2. A semiconductor has a negative temperature coefficient of resistance. This means that the resistance of the semiconductor decreases with increase in temperature and vice versa. For example, germanium is actually an insulator at low temperatures, but it becomes a good conductor at high temperatures. The third property is that when a suitable impurity is added to a semiconductor, its current conducting properties change appreciably. Examples of impurities include arsenic and gallium. We are going to look at two examples of intrinsic semiconductors, which include silicon and germanium. We start with silicon. Silicon is atomic number 14. It has an electronic configuration of 284, and this is the arrangement of electrons: 2 in the innermost energy level. In the second energy level, there are 8 electrons, and in the outermost energy level, there are 4 electrons. The 4 electrons in the outermost energy level are known as valence electrons. We look at germanium. Its atomic number 2 with an electronic configuration of 2 8 18 4. It means that the inner K shell has 2 electrons, the L shell has 8 electrons, the M shell, which is the third energy level, has 18 electrons, and the outermost N shell has 4 electrons. This is the electronic configuration and arrangement of electrons in the atom of germanium. So as you can see, we have 4 valence electrons in the outermost energy level. From there, now we move to bonds in semiconductors. In semiconductors, bonds are formed through sharing of valence electrons. Such bonds are called covalent bonds, and each atom contributes equal number of valence electrons during formation of covalent bonds. This is an example of germanium atoms which have formed 4 covalent bonds through sharing. So as you can see, the center atom has shared electrons, the outermost energy level for the valence electrons with other 4 germanium atoms, and therefore they have formed 4 covalent bonds. These 2 electrons are shared. One is for these center electrons, and the other one is for the adjacent electron. They have formed a bond. They have shared they have shared an electron. So each is contributing an electron to assist in formation of covalent bonds. There is something we need to note. The first one is that covalent bonds are formed by sharing of valence electrons. The second point is that in the formation of covalent bonds, each valence electron of an atom forms direct bond with the valence electrons of the adjacent atom. From there we mention the energy bands in semiconductors. We find that there are 3 energy bands. First one, we have the valence band. Second one, we have conduction band. And then we have the forbidden energy gap. Effect of temperature on semiconductors. At absolute zero, intrinsic semiconductors act as insulators. This is because the valence electrons are engaged in sharing or in the formation of covalent bonds. Therefore, they are not free and they are not able to conduct electric current. Above absolute zero, the valence electrons are released after energy is supplied. The energy breaks the covalent bonds and therefore sets the valence electrons free. And when they become free, they are now able to conduct electric current. We move to conduction in intrinsic semiconductors. We find that in intrinsic semiconductors, there are 2 types of conduction. We have free electrons and free holes. So holes are able to conduct electric current only inside the semiconductor material, whereas electrons are able to conduct current inside the semiconductor is also absent through the cable and the voltage source. In this type of conduction, electrons are moving from the negative terminal of battery towards the positive terminal of the battery, and they pass through the semiconductor material. So electrons are moving from point A, point B to point A, and holes are moving from A towards point B. So this is the conduction of electrons, or the conduction of electric current in intrinsic semiconductors. As we summarize, we have looked at intrinsic semiconductors, what they are, the ion bands contained in intrinsic semiconductors, the effect of temperature in intrinsic semiconductors, and we have described the conduction in intrinsic semiconductors. As we wind up the class, I'm going to give you an assignment so you can write it down. Using a well-labeled diagram, explain the movement of charge carriers in intrinsic semiconductors during conduction of electric current. Thank you, and see you in our next